So, today's lecture will be on floating offshore structures. Now, after that we will go to drilling. There are two types of drilling we will discuss. One is from fixed structure and the other is from the floating platforms. Now, in this diagram, you can see that this is a semi-submersible. Of course, the picture has come out very hazy and you can see the truss and the pontoons. Now, what is to be noted is the very small this BOP. This is your BOP, that blowout preventer assembly. This is down below. So, actually your oil is coming through from other wells and it is led to the semi-submersible. So, this is your the drilling derrick, and here we have your drill string suspended from the crown block that is going right through this marine riser. This is the typical marine riser. This is going down to the, it is connected here to the blowout preventer and top to the deck. So, anyway, so this will come back later on. Now, what is to be noted is the various forms of the floating platforms. So, already we have discussed three types, that is your articulated flare. Come quickly, be seated. Now, here you note that the three types that have already been discussed are the guide tower, then articulated flare is just for igniting your gas, and the TLP. Now, TLP in this diagram you can see the foundations, but what is not been shown is the template. Now, template will come somewhere here, and that is actually the suspension of the pipes, that is, this is called template or a wellhead assembly, which suspends your casings. So, your template is actually a suspension point for the casing string. Template is actually a suspension for casings. So, these are the smaller type of platforms, that is your guide tower, articulated flare. The larger varieties are your TLP and semi-submersible, which are the most common actually. Now, here the guide tower and the articulated flare, these are called compliant structures and also TLP. Compliant category. So, these are also floating structures. So, under this head you come this guide tower, then you have articulated flare, and the last one is the tension leg platform, but do not include semi-submersible under these compliant structures. So, semi-submersible is a fully floating platform. So, these are three types. Now, the reason why you go for this is this equation. Now, in structure analysis you come across this, or sometimes I think in order more appropriate you make this as a vector. K is your stiffness matrix. So, this is your environmental load vector. And this is your underwater structure stiffness. Now, these are all in matrix form. So, any solution to your ocean engineering problem will not be a simple one or two line equations. So, this is called a stiffness matrix. And the last is called the displacement vector. Now, if you look at this equation, you will find that this environmental load vector is coming from the environment. So, this you cannot change. Now, what you can change is this value of k. Now, if you make k small, this being the same, obviously your displacement is going to be large. Now, you have to play around with k. Now, this k matrix, there are two things. One is this reason, what I told you is how much displacement you can accommodate. Now, k is the structure stiffness matrix. Now, k large means the structure scantlings large. So, that is very good, but this also increases your cost. So, increases cost substantially. So, that is why in very deep waters it is preferable not to go for a large underwater truss because of this value of k. K will increase substantially because this displacement. Now, this displacement or the displacement vector, now this actually how much displacement is allowed, how much displacement to be allowed, where allowed on deck. This is the engineering considerations that you have to consider. Because you have too much deck displacement, as you can see in this structure. Now, your guide tower and your articulated flare, obviously there will be no heave motion, but there will be lot of sway motions. There is a lot of sway motions, then that will interfere with your pumps on the deck. So, this is a very crucial question. You see how much deck displacement. I will give you some figures of this deck displacement. So, how much deck displacement to be allowed, that is what you have to decide. So, that basic decision depends on your deck machinery, configurations. So, there are a lot of engineering decision you have to take for design. So, basic equation is this, the k, you have to play around with k. So, one of the reasons I told you is this, that is the scantling of the structures, and the other is your natural frequency, phi is root over what, which you have already learnt. This k is also influencing your natural frequency of oscillation. Now, this you keep p out of omega, that is the forcing frequency. Rather you write forcing wave frequency. So, you can see this stiffness is a very important parameter, both which are related to this p is equal to kx is your static. This is called static offset. Static offset. So, this x is called static offset. Alright. So, you have to find out what is static offset and your frequency, natural frequency. So, these are from the structural engineering point of view, and from the cost considerations. So, this is what I told you, if you have very too much large k, this will also increase your natural frequency, P is equal to, but of course, if you increase k, your mass of the platform will also increase, because you are increasing the weight. So, this P is related both to k and m, but the trouble with k is you are increasing the structure size, especially for deep water. K is very important parameter. So, this is one of the considerations for your compliant, and later on you will find for the floating platform. Now, the floating platform, these are the compliant structures. Your drill ship is a fully floating platform. Drill ship, semi-submersibles. They have nothing, they have no connection with the seabed, whereas you can see your tension leg platform, they are tethered down by means of gravity anchors to the seabed, but these sort of things you will not find in a semi-submersible, they are fully floating. But why you go for this, a fully floating types rather than a compliant one? These are the fully floating varieties. Fully floating platforms. So, you have no business with this P is equal to kx. So, that means the structure will behave like a ship. So, this is no more the case, behavior similar to ships. So, sea motions similar to ships. So, that means in the fully floating case, motions will be large, motions quite large. Motions are very large, especially now in TLP actually we are not having any heave motions. So, in TLP you should remember, in TLP this equation is always valid for all cases of waves, that is the difference between buoyancy and weight is equal to your tension in the tether. So, buoyancy is always greater than weight. Even if TLP is at what? At trough of wave. So, there is always some tension in the tether. Your tethers are always kept under tension. Now, you tell me why you should go for a semi-submersible and not a TLP. The TLP does not have any heave motion. So, only motions that your TLP can have is your sway, side sway will have. But what is the decision between a TLP and a semi-submersible? Now, semi-submersible will have heave motions. Now, heave is the most detrimental motion in case of oil platforms, have heave motions. Now, in order to restrict this, semi-submersibles have what is called a heave compensating device. Actually, you will find semi-submersibles are more common than TLPs worldwide. More common than TLPs. So, TLPs actually mostly you will find in the North Sea. Now, TLP problem will come because of these tethers. Now, tethers have to be anchored. So, normally these are gravity anchors. So, you will find there to be the anchoring of these tethers is a big problem, and also you have to unhook these tethers from your base when there is a storm. So, those are very problematic for your TLPs, but the advantage of a TLP is there is no heave motion, heave is restricted. So, that is why you will find semi-submersibles and drill ships are more common worldwide rather than TLPs. Anyway, so this is one of the considerations that have the engineer has to contend with, and the other one is the BOP location. Now, floating platforms, you remember this, floating platforms always have BOPs located on seabed. This is a great disadvantage actually. They are never placed on the deck of the platform, located on seabed. So, this actually gives rise to remote operation of BOP. Remote operation of BOP necessitated. This is actually very troublesome, because underwater operation of BOP is very tricky and very costly. So, this is the things that are the pros and cons of your TLP and between the floating and the fixed. The other problem is marine riser. Marine riser design. Now, this is the riser design is also not very easy. So, in case of floating platforms, I will show you the figure, because risers have, first thing is for floating platforms, they will have lot of motions. Floating platforms have extensive riser motions. So, this is actually leads to riser rupture. So, this is very critical. Your riser, once it ruptures, then there will be a lot of oil pollution. So, riser motions is a very critical area of study nowadays. Now, this your floating platforms will have lot of riser motions. So, this has to be tackled. How you can control the motion of the platform along with the motion of the risers. So, the problems for floating platforms are essentially motion control. Floating platforms the problems are essentially limiting motions. If you are unable to control motions, then unable to control motions, shutdown operation. Shutdown operations, and this is called weather downtime. This is called weather downtime. So, that means you have to build it for a particular extreme sea state where you have lot of motions. So, this is one of the disadvantages of a floating platform. It suffers lot of weather downtime, that is percentage of the time you are not lifting oil from the oil reservoir, your platform is out of production. So, it suffers lot of weather downtime. Now, the other point, that is, in order, I will give you a brief description of here the three types of platform, that is, all threes are located in the Norwegian sector of the North Sea. So, this is your Stadjord B, this is Magnus, and the other is the Hutton TLP. So, location all are located in the North Sea. Location is North Sea. Just a comparison between different platforms. So, this is the Norwegian sector of the North Sea, and this is the UK sector. And this is again North Sea, North Sea UK. Now, here you have structure type. Structure type, first one is concrete gravity. Next is steel jacket. And the last one is your TLP, that is a tension leg platform. Now, here, so these are type, or rather you can write this is fixed. This one, the steel jacket, is also fixed, and TLP is compliant. Now, you can see the location is more or less the same, that is North Sea. Now, here the water depth is slightly varying. So, structure type actually depends on water depth. Water depth is a very important factor in deciding on the type of structure, whether you go for a fixed, compliant or floating. Now, water depth in this case for the concrete one is 472. Now, your dimensions are in feet. This is steel jacket 611, TLP is 485. Follow. Now here, now 100-year design wave. Hundred-year design wave is, now this is in feet, there is your wave height. So wave height is more or less the same. Here this is 100 feet, this is 102 design wave height, this is 98. So environmental load is more or less the same, you can see, but you can see that the three different structures have been designed: 472 feet, 485, 611. But 611, that is the UK, the British have gone for a jacket type of platform. But anyway, so here production rate. So you have to take certain engineering decisions. This is BPD, barrels per day. I'm not writing the whole thing. BPD means barrels per day. So this is 150,000. This is 120,000. The other one is 110. So you can see TLP production rate is the minimum. The concrete gravity, because it has storage facility, it can store large amount of oil. So BPD is more. So that is one big advantage. You see, these two types of platforms, that is steel jacket TLP, do not have storage capability. So these productions start. They have started production in 1982. So this is 1983 and this is 1984. So this is your Hutton TLP. Now maximum deck offset. Maximum deck offset in this case, gravity you can see is less than 3. So this is given in feet. So gravity platforms is having the minimum deck offset. Jacket 4, whereas TLP is having the maximum, that is 79 feet. Now this you have to take into consideration for your equipments. Cost in billions of dollars at 1982 price. Now this is comparison, this is coming to 1.8. 1.8 is gravity. Jacket cost is the highest, 2.6, and TLP is the minimum. So you can see compliant structure is having the minimum cost, and project you write, this is first one is Mobile, then this is British Petroleum, and this is Conoco. So this is a rough comparison of three types of platform between gravity, steel, jacket and TLP. Now there are various pros and cons. You can see in this case jacket is, water depth is slightly more, 611 is 2.6. So there are certain engineering decisions which you have to take. The biggest is your cost and this deck offset. So how much you can accommodate. So that is one of the biggest challenges you will find, and coming for your platform types. Now platform types, you have in jacket platforms also you will find there are a number of varieties. Jackets, you have tripods, which of course it is not shown here. Then you have this one category. 2, you have extended base. The other type that I have already discussed is your hybrid one. Now, hybrid one is coming under gravity platforms. So, this is a picture of a hybrid one where you have the hexagonal truss and the caisson. There is the cells. Cells are looking, but jackets also have tripod and extended base. Now, extended base, of course, here you can see the diagram of an extended base. Now, this you can see here that the base is made quite large. Instead of this thing being uniform, the base has been widened. So, this is a picture of an extended base. Now, extended base also you can go like this. So, you can build your truss. So, this is your deck, and you can connect it to a extended base. This is called an extended base platform. Extended base to tackle large overturning moment. So, your waves will come somewhere here. So, in order to tackle this overturning moment, you extend base. So, that means your jacket is become very costly for deep water because of this. H for deep water, H will be quite large, overturning moment will be high, and again you have to extend the base, that means jacket extended base. Now, so this is basically for large jackets. Large jackets, the base you can extend. Of course, there will be piles. All these are pile driven. Now, tripod, here before we go to tripod, you can see here there is another sort of structure. This is called a monopile. So, this is also a tripod type of structure. You can see at the seabed there are two cylindrical base that is connected by monopile, and you can call this as a tripod. Now, actually in the Arctic Ocean, in the North Sea, you have structures. This problem we do not have, but in the Arctic actually you will come across ice floes. Arctic Ocean and North Sea, Arctic Ocean, you will come across ice floes. Now, ice floes, they give horizontal forces. So, horizontal forces are very large. Horizontal forces from icebergs, ice floes very large. In order to tackle this, the structure underwater portion sometimes they design in this way. This is your platform. Either you can design it in this way, that is the monopile tripod variety. This is a steel, or you can make the structure like this. I think this is made of concrete. So, there your iceberg comes and breaks on the structure. So, these are some of the structure variations you come across because of variation in the environmental loads. The tripod you also can come across for the marginal field. So, marginal field tripod will be something like this. Basically, you will have 3 legs. So, your truss will look like this. So, this is a marginal field tripod. So, marginal field, where the oil reservoir is very small, you do not have, there is no need to go for a large structure. Here you can go for a small jacket structure. So, these are some of the considerations that you will come across. So, this is the first one is a extended base, then this is a tripod for marginal field, and here also you can go for another, this is called a monopile actually. There is a single column supported by a underwater truss. So, these are some of the variations in the jacket structures you can come across. Now, next, before we discuss about drilling, so drilling 2 types. So, basic, the number 1 is drilling from fixed platform. The other one is drilling from floating platform. So, what is your engineering decision for building your structures? Now, in case of offshore structures, so these are the engineering decisions that you have to come across is so you are going to be an ocean engineer, you have to make what is called engineering decisions. So, what are the major engineering decisions? Number 1, the major engineering decisions are motion restrictions. As a naval architect, ocean engineer, this is a prime area of study. 2, engineering decisions of platform design, of platform, rather you write of platform type. 2 is what? Environmental load intensity. That is why I talked about the wave, that is the wave spectra. Environmental load incident, motions, environmental loads. 3, production rate BPD. There are 3 very important parameters I am telling you. This is for platform design. Four, just now talked about water depth. Water depth is also a very important parameter designing whether you go for floating or fixed. Now, actually you will find all this depends on the engineering capability of the contractor. If you do not have expertise in floating platforms, you do not go, because then you will be in soup. The last one is cost. And this goes along with cost is risk. How much risk you can take, risk of failure of structure, because from this you will find insurance cost. The insurance cost is very high. Insurance cost can go as high as 10% of project cost. So, these are the major decisions you have to take if you are a platform designer. So, a lot of technology, cost and risk are to be taken into account. So, there are 6 parameters which will come. Now, the last one which I am going to tell you is related to your drilling operations. Now, before you go to drilling, we have to study what is exploration. Exploration and extraction of oil. So, that means before one goes to extract oil from the oil reservoir, I told you one parameter, that is the production rate. You have to decide on the production rate, number 3. Now, this decision you have to take oil reservoir. Oil reservoir, that is quantity of oil. Now, you can see the price, that is the cost I have told you, that is in 1983. 1983 figure we are getting something like 1.3, 1.8 some millions of, or rather billions of dollars. Now, if you can project it in 2010, you just can imagine it will be something like 20 or 50 billion dollars. Sometimes this goes more than a nuclear plant. Now, who is going to foot the bill? So, prior to that you have to make lot of analysis. Now, this actually you have to get the quantity of oil in the reservoir. So, this is actually done by geophysicists. Now, they tell you whether at all you go for oil exploration in deep water or in under the sea or not. Depends on the quantity of oil in the reservoir. Now, this is actually done geophysicist, or rather you write geophysical exploration has to be done. Now, there is a company which specializes in this geophysical exploration. The oil companies have given you the names, that is Mobil, Exxon, Conoco, and this is a specialist job. This is done by Schlumberger. They are the specialist in oil exploration. So, now they will tell you about reservoir rocks. So, before you take the plunge into billions of dollars or sink billions of dollars in the sea, you have to study the rock formations. These are oil you will find in sandstones. Porous and permeable. So, I am not telling you in detail, but since these are for your information, and these reservoir rocks you will find in this formation. So, this is your seabed, and this is called reservoir rocks. So, this is called a cap of reservoir rocks. Now, here you will find, first you will find natural gas on top of oil. Oil you will find here, and salt water will be below. You will find in this order, but essentially oil you will find a cap of reservoir rocks. Now, these geologists, they will be doing survey. Survey work has to be done before you go for your platforms. Geological mapping. So, map, basically you have to map rock formations. So, these are done by aeroplanes. They make a survey, you measure this angle of dip and strike. These are the various rock formations. Number 1, number 2, oil is to be found in faults in the rock formations. Anyway, so this is geological mapping. The other type of mapping that is done is geophysical. Geophysical, you measure what is called gravimetric force. Variation in the G. Variation of G in reservoir. Suddenly, if you find that there is variation of G in the oil reservoir, then that shows there is presence of oil. Other one is seismic. This is called seismic survey. Explosions from floating ships, or rather you write trigger explosions on seabed rock formations. From floating ships. Measure penetration of seismic waves. So, like this you can map the rock formation. So, this is called a seismic survey. The last survey is called a magnetic survey. So, these are the different forms of survey work which is normally done. So, this actually measures variation in the geomagnetic properties, measures variation in geomagnetic properties. Now, after all this is done, now basically nowadays all this information is led into a computer. So, information processed by computer. Now, in this computer you can get a 3-dimensional portrayal. Reservoir. So, this information is supplied by your geophysicist by doing all these 3 kinds of survey: gravimetric, seismic, magnetic. So, in the computer you will get a 3D plot of the reservoir. After this you do what is called a geological survey. So, remember all this survey work has to be done because you are pumping billions of dollars of money into the seabed. You better be sure. Geological survey, that is lift core samples from ocean rock strata. And analyze in laboratory. For quantity of oil. Now, this is done from drill ship. This is the last survey, that is your geological survey. So, all these various stages of survey work have to be done before you go for the next stage. What is the next stage? So, this stage is called exploratory drilling. After this, you go for production. So, this in the next class we will discuss this. There are two methods of drilling. So, this is how you go for your to lift oil from your seabed. Okay, thank you.